Let's start this off with an interesting story. Long ago, people were obsessed with what was called alchemy, and it was kind of a quasi science. People would do things that looked like chemistry, but it was all very mysterious, not really based on results of the senses or the natural world. But in this pursuit of alchemy, one of the key ideas was to be able to turn one material into another. And kind of one of the key materials that these alchemists were most interested in is, could we turn lead into gold? Clearly, having lots of gold made you rich and powerful. So, this ability to convert lead, which was cheap and easy to get, into gold would be highly sought after. Now, thinking about this, that seems like, oh, this is like some sort of magic hocus pocus. But interestingly enough, what we see with radiation and changes in the nucleus is essentially this. Now, it's not turning lead into gold necessarily, but nuclear decay can turn one element into another completely different element. Let's take a look at some examples of how that can work. Our first example of this, let's take a look at alpha radiation. As you guys should have seen in your notes, in alpha radiation, 2 protons and 2 neutrons are shot out of the nucleus as one full chunk. Now, if you're looking at your periodic table by chance, you might notice that this is exactly the same thing as a helium nucleus. And in fact, it's often referred to as a helium nucleus, and if this chunk slowed down or for some reason was able to pick up a couple electrons, it would be indistinguishable from another helium atom. So that's alpha decay. Now, what we want to focus on is what happens back here to the nucleus that it was shot out of. Alpha decay often happens with large unstable nuclei. So for example, let's look at uranium 238. Now, for all of these questions, you're going to need to look at a periodic table. So I'm going to just draw a little picture of the information we need for this scenario. You take a look at the periodic table. Uranium has an atomic number of 92 and a mass of about 238. There's probably some decimals here, but we're going to think specifically about this one. Now, if uranium-238, this nucleus right here, emits an alpha particle, what happens to this nucleus? Is it still going to be uranium-238? No, of course not. It can't be. It's losing protons, and protons define the element. So if 2 protons go shooting out of here, this is no longer uranium. What has it become? If you look on the periodic table, we would need to find an element that is not 92, but in fact 2 less, 90. So we're now looking for one of the elements on the table that has an atomic number of 90. Doesn't matter what the mass number is because atomic number defines the element. And you will notice that atomic number 90 is thorium. Now, we're not going to just write the mass down from the periodic table because remember, periodic table mass is just an average. We know what the mass will be. We started with uranium-238. That number 238 is a total, a sum of the protons and the neutrons in this original nucleus. And how many things flew out? Right there, 4. So if 4 shoot out, that number will drop by 4, and this would be uranium-234. So, if the question said uranium-238 emits an alpha particle, what does the uranium become? The answer is thorium-234. It actually changes elements because of the radiation that it emits. Now, often this decay continues. Thorium-234 might still be unstable, and it might undergo decay. Maybe it's alpha, maybe it's beta. We'll save that for another time. But the key idea here is, with an alpha decay, you have a new element due to the changed proton number. kind of like what those alchemists were trying to do with turning lead into gold. In beta decay, a negative particle is shot out of the nucleus, and that should seem weird because there's no negatives in there. There's only protons and neutrons. So to explain this, what we're essentially saying is that a neutron somehow emits a bit of negativity, and that leaves a positive particle. To put that into simple terms, it's kind of like thinking that the neutron is really like a proton and an electron merged together. And so if it emits the electron, what's left is a proton. Now, notice like the notes say here, the nucleus has the same total number of particles because we turned a neutron into a proton. We didn't lose a neutron. We didn't lose a proton. It was like a trade. So the total mass number is the same, but the proton number is different. And if the proton number is different, we have a different element. So let's try an example here. Let's do a problem with this. Let's say we have, oh, I don't know. We'll go with what I had from last time. We had thorium-234. Thorium has an atomic number of 90. And that's important because we need to know proton number. So if this thorium, we're saying this nucleus over here was thorium-234, and it emits a beta particle, it's going to have a neutron converted into a proton. So how do we know what element it's going to be? Well, the element is defined by the proton number. And the proton number will no longer be 90. It will be 91. One more than what it had before. Now, how did it get that one? Again, it was a neutron converted into a proton. But since the mass number, this number down here, is just a total count, we would say, yes, you lost a neutron, but then you gained a proton. So this is still 234. So now all we have to do is look on the periodic table to find whatever has 91 protons in it. The element on the periodic table that has 91 protons is protactinium, which you will notice is Pa on the periodic table. So again, this is tying back to that idea from the very beginning. Can we have one element completely change into a different element? Yes, as long as that nucleus was unstable to begin with. The forces in the nucleus were out of whack, causing radioactivity, which just means that some kind of particle is going to fly out of the nucleus. In this case, it was a beta particle, converting a neutron into a proton and changing thorium-234 into protactinium-234. But beta and alpha are not the only ones. Let's look at the next one. Gamma is next up for discussion here. Now, let's take a look here. In gamma decay, the stuff that's actually shot from the nucleus is a wave of electromagnetic radiation. Well, that's not a particle. Does that change the proton number? No. Does that change the neutron number? No. It is, as you can see in this kind of model of what we think is happening here, a wave of electromagnetism. It's essentially saying that this nucleus has a lot of energy, like too much energy, and it's jiggling back and forth and getting all crazy, and it emits that energy as a little bit of gamma radiation, and that lowers the energy. But it does not change the nucleus to a new element because it has not changed the proton or neutron number. Gamma often accompanies other kinds of radiation because when those particles get shot out, that causes a difference in energy, and that energy can be emitted as a gamma ray. All right, everybody, we're finally to the last one. The last one is called positron emission. Sometimes you'll see this referred to as beta plus radiation because it's a lot like beta, but instead of being a negative particle, it's a positive one. So if we look at our description here, it says in positron emission, a positive particle is shot from the nucleus, but it's not a proton. The idea here is that the proton somehow like shoots a tiny little positive chunk out of it, and what's left over is neutral. Now this is kind of weird. It's like some kind of particle, the size and kind of characteristics of an electron, super tiny, super light, but positive. And when that proton shoots it out, what's left is pretty much like the proton was, but it's now neutral, which would pretty much make it a neutron. And that's what's happening here. We have a positive particle that flies out, kind of like a positive electron, converting a proton into a neutron. Now, the million-dollar question, will this change the element? And hopefully you've gotten the idea that yes, it will, because it is causing a different number of protons. In this example, we would have less protons now because we converted a proton into a neutron. So we'll continue with the example from before and say that we have protactinium 234. Protactinium has that atomic number of 91. 234 was the mass number of this particular isotope due to what we knew before. And now we're saying it's not going to be this anymore because of the positron emission. What's it going to be? So if we start out with the numbers that we have and say those numbers are going to change. If we convert a proton into a neutron, what's going to happen to the proton number? It's not going to be 91 anymore. We're going to lose a proton, essentially. So this is going to drop to 90. But this is going to convert into a neutron. So it's like kind of like losing one from here and then gaining one from here, which means the total number is still the same, just like it was with beta. So this is still a mass number of 234. And now we're at 90 again, which is back to thorium. Which makes total sense because we got to protactinium because of beta decay. And we just said that a positron emission is like beta but an opposite charge. So it basically put us back. Now we would have this element here, thorium-234. Now, it would be highly, highly unlikely that in nature this particular chain of decays would happen. The chain of decays that happen is due to the forces in the nucleus. And the forces in the nucleus being out of whack causes particles to be shot out. But it's not going to bounce back and forth and shoot a beta and then a positron and then a beta. It's not random. Okay, those are all 4 kinds of radiation types and what they do to the nucleus of an atom. Pretty cool when we tie it all the way back to the beginning there with alchemy, this idea of somehow changing one nucleus into another, changing one element into something totally different. And it happens all the time with radiation and radioactivity.